Okay, so we have our Lewis structure here. All bonds explicitly represented. In our bond line structure, we have the same information conveyed, but just in a more condensed format. All right? So, where are those 3 carbons? Our carbons are at the endpoints and intersections. All right, so the endpoints of these line segments here and here, there are carbon atoms there. And at the intersection of these line segments, we got a carbon atom. Right? So that little asterisk, that little 2-line triangle there is our propane, representing those 3 carbons, again at endpoints and intersections. Okay? So then what about the hydrogens? How do I know how many hydrogens there are on each of those carbon atoms? The full octet, absolutely, right? So the key here is that carbon likes to have 4 bonds. So hydrogens we fill in to make 4 bonds per carbon. All right, so those hydrogens are just implied. Hydrogens always kind of decorate the outside of your molecule. So if I'm looking here, I have this carbon at the end that has only 1 bond, so I'm going to need to fill that in with 1, 2, 3. The other end, same thing. I only got 1 bond represented, so I'm going to have to fill that in with 3 hydrogens. The carbon in the middle currently has 2 bonds, so it only needs 2 more hydrogens. Okay? These bond line structures you're going to see over and over and over again. That's how we represent our structures in organic chemistry. That's what we need to be really good about, both reading and drawing. Okay? So step 1 here, just to review, I'm going to put down some bond line structures, and you're going to tell me how many carbons and hydrogens and oxygens, if they're in there, whatever. You're going to give me the molecular formula for these compounds. All right, these are both just hydrocarbons. We'll start there. So C what, H what? What subscript should go right here? How many carbons and how many hydrogens do I have in each of these molecules? All right, so let's look at this first one. How many carbons we got? We got this endpoint, this intersection, endpoint, endpoint, right? All endpoints and intersections. So we have a total of 5 carbons, okay? If we're gonna go through, we gotta fill in our hydrogens. And again, the principle is carbon likes to have 4 bonds. So we're gonna just fill in hydrogens to make sure carbon has 4 bonds. So there should be 3 on these terminal carbons here, the ones at the end. Okay, how many on this carbon right here? We need 2. And what about this one in the middle? Just 1, right? Because we got 3 bonds explicitly represented. So 1 here. So that's what? 3, 6, 9, 12. So C5H12. Okay, just to use this same example, all right, I called these terminal carbons, the ones that are at the end here. We have another sort of special name that we use. What do we call a carbon that has only 1 carbon neighbor? Primary, absolutely, a primary carbon. Well, 1 with the degree sign there, meaning 1 carbon neighbor. All right, this one we said had 2 hydrogens and 2 carbon neighbors. What do we call that? Secondary, meaning 2 carbon neighbors. And that one in the very middle here that has 3 carbon neighbors, we would call that a tertiary carbon. 3 carbon neighbors. All right, and these classifications are helpful because it turns out that for some reactions, primary carbons behave differently than secondary carbons, behave differently than tertiary carbons, right? So we have this sort of designation. And really what we're talking about with our designation here is how many other carbon neighbors does it have? I guess just to be good, we can do one more. We have the little plus sign here. This carbon in the middle has 4 carbons, 4 carbon neighbors, so it doesn't need any hydrogens. This would be what we would call a quaternary carbon. Cool. All right, so now we're going to go back to this molecule here. This is, again, just carbons and hydrogens, but now we have some double bonds and some triple bonds in here. Or a double bond and a triple bond. So first of all, how many carbons am I looking at? Okay, so we got our endpoints here. These are pretty straightforward. 1, 2, 3, 4, 5. This one, the one that everybody forgets about, is the one on the other side of this triple bond here, right? That triple bond exists between 2 carbon atoms. So indeed, yes, I have a total of 7 carbons in this structure. Okay. Now, when we are adding in our hydrogens, those triple bonds, they count towards the number of bonds that those carbon atoms have. All right, so if we look here at our easy primary carbons, we can fill in these each have 3. Okay, we have this one up top here, 2. But now let's look about this double and this triple bond here. How many hydrogens should I fill in on this carbon sticking off the end of my triple bond? 1. Just 1. Right? This carbon already has 1, 2, 3 bonds associated with it, so it only needs 1 hydrogen to complete its octet. What about on the other side of this triple bond? How many hydrogens? Who says 1? Who says 2? Trick question. How many? 0. Excellent. Okay, there are no hydrogens there, right? Because we already got a total of 4 bonds going on for that carbon. Likewise here, if we look at this carbon, we already have 1, 2, 3, 4 bonds associated with that carbon, so there are no hydrogens there. All right, and then lastly, this carbon right here, how many hydrogens? Just 1. Okay? And so when you look at these bond line structures, you kind of want to, in your mind's eye, be able to fill in where those hydrogens are, because again, they're just implied by the structure. So it's 6, 9, 10. So C7H10. Okay, cool. All right, so now I'm going to give you a molecular formula, and you're going to draw me just any structure that matches that molecular formula. Okay? C3H8O. Give me any molecule at all that matches that molecular formula. All right, and if you're looking for bonus points, there are 3 that you could draw. No, you don't. All right, so first thing I'm going to do is I'm going to draw my 3 carbons. Okay. I'm going to put in my oxygen, right? So for these what we call heteroatoms, everything that isn't carbon or hydrogen, we do have to explicitly represent that. You could just put OH, that's fine. You could draw the actual OH bond in, that's cool. All right. So this would be one such structure that matches this formula here. You can go through and convince yourself. We got 1, 2, 3 hydrogens over here, 4, 5, 6, 7, and then finally that last one on my oxygen makes 8. Okay. There is something missing from this structure here if I'm being really good about drawing a complete bond line structure. What am I missing specifically on that oxygen? Lone pairs. Okay. Oxygen likes to have 2 bonds and 2 lone pairs. All right, remember we represent that as those pair of dots. These lone pairs, especially when you get more advanced in organic chemistry, you get really lazy and you stop drawing them in there, which is a little bit of a detriment to students and their understanding because those lone pairs are absolutely crucial for the chemistry of those molecules, right? The attacking of a nucleophile is because of a lone pair on that molecule, okay? If I'm going for another one of my structures here, I could just move that OH group to carbon 2. Okay. All right, I'm not going to go too much into it. Again, if we need you need review of functional groups, there's that posted video, but both of these molecules share the same functional group, that OH group. What do we call those? What is it? Alcohols, right? OH. These would be a pair of alcohols here. Okay, and I told you that there was 3 structures. Does anybody know what the third one is? I'll give you a hint. It is not an alcohol. Yes, absolutely. If I move that oxygen in between 2 carbons, All right, so instead of connecting all 3 carbons, I'm going to stick an oxygen in the middle there. Okay, this is no longer an alcohol because there's not an OH group. There's a carbon on either side, and this is an ether. Okay, and just some fun terminology from the first semester, because these all share the same molecular formula but are different structures. These are all what we call constitutional isomers. Okay, so we can just say same formula, different structures. Cool. All right. So again, these lone pairs are going to be really important. Again, you'll see a lot flipping through your textbook or looking online at different resources. Places get lazy and they don't put them in there. That's because we know that if oxygen has 2 bonds, it always has those 2 lone pairs. It needs its complete octet. All right. So real quick, let's just go back. Looking at the periodic table, you can sort of tell how many bonds and how many lone pairs a particular element likes to have. All right. I don't know where a periodic table is. I know I got a million here. Hold on. Here we go. Ignore all this. All right, so first of all, organic chemistry, we are very much so concerned with this half of the periodic table over here, right? We spend very little time talking about the metals, transition metals, right? Only sort of in passing. We are very much so focused on these non-metals because those are the one that forms covalent bonds, all right? So by looking at an element's position on the periodic table, we can tell how many bonds and how many lone pairs we should be drawing in, okay? So number of bonds, we'll keep track of that up here, and number of lone pairs. Carbon, we said, likes to have how many bonds? 4, and then how many lone pairs? None. All of those electrons are in those covalent bonds. And as we go over, we're going to see number of bonds decrease, number of lone pairs go up, right? So nitrogen likes to have 3 bonds, but again, needs that complete octet, so it will have 1 lone pair. Oxygen likes to have 2 bonds and 2 lone pairs. Our halogens, which we do talk about quite a bit, they only like to have 1 bond and then 3 lone pairs. And we don't talk about these noble gases at all, because they're noble. All right? But so just by looking at where an element lies on the periodic table, if you have a sort of normal structure, you can know how many bonds and how many lone pairs that particular element should have, right? So that's why our alcohol here, our oxygen, we had those 2 bonds and we filled it in with those 2 lone pairs. Cool. But of course, it's never just that easy, which brings us to our next important topic here, formal charges. All right. Oftentimes, the most stable form of a molecule does not have any formal charges in there. Okay? Those are by far, molecules don't really like to have formal charges. Bearing a formal charge like a net negative or a net positive charge will necessarily come with an increase in energy. All right, but nonetheless, reactions usually proceed through high energy intermediates, which indeed do have formal charges associated with them. All right, so let's just look at a few examples here. We said that oxygen, if we just draw an alcohol group here, it likes to have 2 bonds and 2 lone pairs, which means that its formal charge is 0. That's what we mean when we say likes to have. All right. So let's just make a little cheat sheet here. Formal charge. Number of bonds. Number of lone pairs. Again, likes to have, meaning it has a formal charge of 0. That's 2 bonds and 2 lone pairs. So what if I take away one of those bonds? All right, so we see an oxygen that just has one single bond associated with it. All right, so first of all, if it's only got this little random looking lollipop thing, it's only got one bond associated, but of course oxygen has to have its complete octet. So how many lone pairs am I going to fill in around this oxygen? 3, because I got to make it a total of 8 electrons. So now we have 1 bond and 3 lone pairs, right? So I've replaced one of my bonds with a lone pair. This oxygen then has a formal charge of -1. All right, so we would represent that with a little negative sign next to that oxygen. All right, so if we replace a bond with a lone pair, we go down in our formal charge. And if I did the exact opposite, and I replaced one of those lone pairs with a bond, so I'm going to protonate this oxygen here. Now I have 3 bonds explicitly drawn, so how many lone pairs should I fill in? Just 1. All right, and now I've replaced one of my lone pairs with a bond, which means I increase my formal charge to +1. So again, we'd represent with a little positive sign. All right, so let's do nitrogen. I want you guys to fill this in on your own here. First of all, we said that nitrogen likes to have 3 bonds and 1 lone pair. So when we say likes to have, that means that if it has 3 bonds and 1 lone pair, its formal charge would be 0. So I want you to tell me what would happen if we decreased the number of bonds and increased the number of lone pairs, or increased the number of bonds and decreased the number of lone pairs. Everybody take a second to fill out this chart here for our nitrogen formal charges. So I'm going to draw my nitrogen with 2 bonds and 2 lone pairs. What formal charge should I be filling in? Who thinks it's -1? Raise your hand. Okay. Cool. Right, so same pattern. If we replace a bond with a lone pair, that'll decrease our formal charge. So put a little minus sign there. If we replace a lone pair with a bond, I'm going to increase my formal charge. Okay, and so it's a good idea in your notes to go ahead and pick one of those halogens, chlorine, fluorine, or bromine, and play the same game. The last element that I want to make sure to explicitly go over is carbon, because carbon is a little bit of an oddball, all right? What I want you to notice about these these 2 tables that we just created is if you sum up the number of bonding electrons and the number of lone pair electrons in every single one of these columns on this table, you will always get those 8 electrons, that full octet, right? So nitrogen and oxygen never break their octet. Right? When you're doing your electron pushing arrows, when you're shuffling stuff around, you need to make sure that those 2 elements always have a complete octet. They will never be left with just 6 electrons ever. Not going to happen. Okay? Carbon is a little bit of a weird one, though. An exception to that rule. All right, so first of all, if we draw carbon with a formal charge of 0, that's 4 bonds and no lone pairs. If we go down in bonds and up in lone pairs, what would we expect our formal charge to be? Is it going to go up or down? It's going to go down. So this would be a carbon with a -1 charge. Because it's carbon and carbon is the star of organic chemistry, we have a special name for these carbons with their -1 charge. This would be a carbanion. Carbanions are super duper unstable. Nonetheless, you will see them as intermediates in reactions, right? High energy intermediates in a reaction. Okay, we can also have a carbon with a +1 formal charge. But now I can't sort of follow my same trend before of replacing a lone pair with a bond because it didn't have any lone pairs to begin with, right? So a carbon with a positive charge here has 3 bonds and no lone pairs. We again have a special name for these positively charged carbons. These are carbocations. All right, and carbocations are the only species you're going to see in organic chemistry that have incomplete octets. Notice that this carbocation has 3 bonds but no lone pairs. So there are only 6 electrons in its octet. So we can just note carbocations have incomplete octets. All right, so they're not very stable, but they're, again, very commonly seen as intermediates in chemical reactions, those high energy intermediates. All right, and again, this is going to be the only time you see something breaking the octet rule is forming a carbocation. Cool. All right, so these are important to spy because charges are something that's notoriously difficult to manage in a chemical reaction. All right, so now let's look at some reactions, and in particular, we're going to look at some reaction mechanisms. AKA, what we need to know are electron pushing arrows. All right, so one of the first types of reactions that you covered in organic chemistry, and it was a good place to start because it's sort of type of reaction that you cover in all levels of chemistry are acid-base reactions. All right, so let's look at an acid-base reaction, and in particular be very good at looking at structures. We're going to take hydrochloric acid. And a hydroxide ion. Okay. Looking at my hydrochloric acid real quick, because my chlorine is a halogen. How many bonds do the halogens like to have? Just 1. And so how many lone pairs should I be filling in on that chlorine? 3. Okay. My hydroxide is actually an ion, so this has a net negative charge, and that negative charge lives on that oxygen, so I'm going to fill in those 3 lone pairs and that minus sign. Okay. My hydrochloric acid would be, you guessed it, an acid in this reaction. The hydroxide would play the role of a base. Everybody take a second and see if you can't remember what the products of this reaction would be, this acid-base reaction. Remember, acids, they donate their protons, and bases, they accept their protons. Can anybody tell me what one of my products is going to be? Absolutely. So one product here will be water. So let's say that I remember that. My acid and my hydroxide should give me water. I'm going to fill in my proper number of lone pairs here. Okay. What's my other product going to be? Let's just play the spot the difference game. What do I have represented on the left that I do not see represented on the right? That chlorine. Okay. How many lone pairs should there be on that chlorine? 4. It's all by itself, no bonds, meaning it should have 4 lone pairs. Okay? Now there's something missing here from my chemical equation. What is that? That minus sign, right? So let's just note, in our reactions here, we will have this conservation of charges. You will always see this. Charges, again, are notoriously easy to kind of mix up throughout the course of your reaction here. If I look on the left, I have HCl, which is neutral, and a hydroxide, which has a minus sign. If I look on my right, there better be a minus sign there somewhere. I have to have the same net charge on both sides of my chemical equation. In this case, if we go back and we looked at our, sort of filled in our chart for chlorine here, we would see that when chlorine has no bonds and 4 lone pairs, it has this -1 formal charge. Okay, so here is my chemical equation. I have everything on the left represented on the right. Everything's all balanced. All right, so let's take a look, because, you know, in organic chemistry, it's not necessarily just enough to know like what's going to be the products. Oftentimes we know the mechanism for our reaction, what's happening to our electrons throughout the course of our reaction here. If we look, we can see a shuffling of electrons. There are electrons that used to be bonding electrons that are now lone pairs. There are electrons that used to be lone pairs that are now bonding electrons. Okay? So in particular, if I look on my chlorine, I see on the left it has 4 lone pairs. Nope. On the left, it has 3 lone pairs, and on the right, it has 4 lone pairs. Where the heck did this extra lone pair of electrons come from? Absolutely, this is my bonding pair of electrons over here. Okay? Likewise, if I look at my hydroxide ion, on the left, there are 3 pairs of electrons, and in water, there's just 2. So where did this lone pair go? It became this bonding pair of electrons, right? So in our chemical equation, not only do we have all of our atoms represented, I have the same number of oxygen, hydrogens, and chlorines on both sides. I also have the same number of electrons on both sides. And the electrons are the interesting bit. That's what's being arranged when we do our chemical reaction, okay? So we can show this movement of electrons using these electron pushing arrows, all right? So I'm going to just start over here. Okay, and I'm going to use electron pushing arrows to show my new bond being formed. All right, so starting at this lone pair here. Okay, where should this arrow point to? To the hydrogen, to this, where this new bond is being formed is with this hydrogen atom. So it's got to reach over and grab that hydrogen there. All right, this would be a bond formation arrow. I'm starting at a lone pair. I'm ending at an atom that's creating a new bond between the oxygen and the hydrogen. And I got to put in one more arrow here. That shows this bond right here breaking. This pair of electrons is going to jump up onto that chlorine atom there. Okay, so this now starts at a bond and ends at an atom. This would be bond breaking. And that leads to my products, water and the chloride ion. Okay? These electron pushing arrows are both a very tricky part of organic chemistry, but they're really important because they're how we show even more detail about a chemical reaction, right? It's one thing to mix 2 things together and figure out what the product is. It's quite another thing to know how the electrons are actually moving around in a reaction, all right? And so some reactions, all we care about are what the products are. But then there's a lot of reactions that we study even more in-depthly, and we learn the mechanism of those reactions, how the electrons are being shuffled around. importantly for our electron pushing arrows, right? We have this arrow here. The base of the arrow always has to be at a pair of electrons. All right, so what you want to convince yourself of is, in our above example, is both of these electron pushing arrows, they start at a pair of electrons. So that could either be a lone pair or a bonding pair, but they're always starting at a pair of electrons. All right, and in my mind's eye, what I'm thinking of when I'm seeing these arrows is that pair of electrons is being dragged over to the tip of the arrow, which is always pointing at an atom that's going to be accepting those electrons. Right? So we said this lone pair, if we look above, we sort of color-coded our electrons and how they were moving, and then we displayed the exact same thing using our electron pushing arrows. It's this pair of electrons on the oxygen that's reaching out and grabbing that hydrogen. Likewise, we have this pair of electrons that used to be shared between between chlorine and hydrogen that is now being dragged onto just that chlorine atom, or I guess now it's a chlorine ion. Okay, but when you draw your pair of when you draw your electron pushing arrows, again, the base is always at a pair of electrons, and the head of the arrow is always at the atom that's accepting those electrons. Okay, so I'm going to put down a few examples of electron pushing arrows, and I want you to follow them. I want you to draw what's going to be on the other side, and then we'll sort of do the reverse. All right? All right, so if we look at this top one, we only have one electron pushing arrow here. All right, so we see that the base of this arrow is at a lone pair, and it's pointing to a carbon atom. The head of your arrow will always be pointing at an atom. Okay, so what is this electron pushing arrow representing? A bond being broken or a new bond being formed? So this would be bond formation. This lone pair is now becoming a bonding pair of electrons. All right, so I need to draw a new carbon-oxygen bond. Doesn't really matter where along the lines you put it here. I'm going to put it at the bottom. Doesn't really matter. Could have put it on the side, same molecule. All right. What do I need to finish off my product here? Lone pairs, and in particular, how many lone pairs? Just two, because it already has those two bonds associated with it. But if I look on the left here, I had 3 lone pairs. What happens to this lone pair over here? It becomes my bond. It becomes this covalent bond. Okay? And then what about my charge conservation? Because I have a carbocation on the left, and I have this hydroxide ion, right? So I have a positive charge and a negative charge. So why don't I have positives and negative charges on the right-hand side? It's the net charge that I got to pay attention to, right? So the net charge on the, yes, I have a positive charge, but I also have a negative charge, so I have a net charge of 0. So then it checks out that I have a net charge of 0 on my right-hand side as well. Okay. All right, so now we got two. We got 2 things going on at the same time here. Okay, this first arrow starts at a lone pair. And ends at a carbon atom. All right, this pair, this line right here. So what does that represent? A bond being broken or a bond being formed? So again, if we're starting at a lone pair and we're ending at an atom, that would be a bond formation. But what about over here? Now I'm starting my arrow at a bonding pair, and I'm ending at this oxygen atom. So what does this arrow represent? So this would be bond breaking. That pair of electrons in that covalent bond is going to jump up on that oxygen and become a lone pair. So this would be a bond breaking arrow. So I got both of these things happening at once. Okay? So when we're drawing our products here, one very easy way to make sure that you haven't messed anything up is counting carbons, right? How many carbons do I have on the left-hand side? 3. So how many carbons should I have on the right-hand side? 3. Make sure that all 3 of those carbons are represented. Okay, I have this oxygen was single bonded. That was a little weird. All right, what else do I need to do? I need to add that extra bond, right? I've created a new bond, so now we have a carbon-oxygen double bond. And since oxygen has its 2 bonds, how many lone pairs should I fill in? 2. Does anybody remember what special name we have for these carbon-oxygen bonds? Holy hell, are they going to play an outsized role in this semester? I can't even tell you. We haven't really gotten to those functional groups. The alkenes, the ketones, the carboxylic acids, all that jazz. That is in this semester. We're going to talk about these freaking carbonyl bonds till we're blue in the face here, all right? But yes, these carbon-oxygen double bonds, these are what we call carbonyl bonds. I guess I lied. I don't have 3 carbons on the left-hand side. I have 4. What happened to this one? All right, so now I've broken this bond right here. So now I have separate my oxygen and its carbon. Okay, and what happened to this pair of electrons that used to be in this carbon-oxygen bond? Where is it now? Sitting as a lone pair on my oxygen. Cool, so I'm done? What's wrong? Yep. So what's my net charge on my left-hand side? -1, so I better have a net charge of -1 on my right-hand side. Where does that net charge live? On that oxygen with its 1 bond and its 3 lone pairs, right? That's our signature for a formal charge of -1. Okay? So we have these bond formation arrows where you start at a lone pair and end at an atom that's creating a new bond. If we start at a bonding pair of electrons, then we're going to be breaking that bond. Okay? There's one last type of arrow that we see, and we're going to see this a lot because, again, our first chapter is talking again about alkenes. Okay. This is from everybody's favorite reaction mechanism here, the hydrohalogenation of an alkene. Okay, I want everybody to take a second and draw me the product of this step in my reaction mechanism. All right, and pay careful attention to your formal charges here, your conservation of charges. All right, so let's look at this bromine first. If I'm going to draw my bromine on this side, it had 1, 2, 3 lone pairs on my reactant side. How many should it have on my product side? Who thinks 3 still? Who thinks an extra lone pair? Okay, cool. So where did that extra lone pair come from? From that bond, right? It accepted this pair of electrons here. And if bromine has 4 lone pairs, what should be its formal charge? -1. Cool. All right, so the hard bit is what's going on the other side here. Let's draw in our 3 carbons. Okay. This arrow here, which started at a pi bond and ended at this hydrogen atom, this actually represents 2 things happening at the same time. First, we're breaking that carbon-carbon double bond. I guess we should specifically say the pi bond. Okay, so this would be representing a bond breaking between carbon and carbon, but we're also forming a new carbon-hydrogen bond. Right? So this is both bond breaking and bond formation all in one step when we're starting at a pi bond. So I have a new carbon-hydrogen bond, and of course we can leave hydrogens implicitly represented, but just for the sake of clarity, I'm going to draw it explicitly here. Okay? And then I'm done. What's wrong? Charges, right? Again, charges, such a pain in the butt, but if we're careful and we look back, it was kind of easy to see how that bromine got its negative charge, right? It accepted that pair of electrons. But if we look, we have a net neutral charge on the reactant side. We have this -1 side on the product side. That means there has to be a plus sign there somewhere. Where does that plus sign go? On a carbon, right? What we call a carbocation. Okay, and in particular, this carbon, this pair of electrons that used to be shared between these 2 carbon atoms is now got snatched away from one of it, leaving it with an incomplete octet or a carbocation. Cool. So managing charges going to be tricky. All right. Cool, so that's where we're following our electron pushing arrows, right? If I draw a mechanism step and I put in these electron pushing arrows, you can give me the result of that step, all right? So now I'm going to give you the before and after, and you're going to draw in those electron pushing arrows. All right, I'm also going to be asked and leave off formal charges here, so fill in these formal charges where they're needed. All right, so if we're going to play this like spot the difference game, if we look at our nitrogen, we have a lone pair on the left-hand side. And we don't have a lone pair, we have a new bond on the right-hand side, right? So those are the same pair of electrons. Likewise, if we look on our oxygen, we have a lone pair on the right-hand side, 3 lone pairs, but only 2 on the left hand and this extra bond, so those are going to be the same pair of electrons. So how many arrows am I going to need to put in here to finish off this mechanism? 2. I need 1, that's my bond formation arrow, right? Forming that new bond between the nitrogen and the hydrogen. Again, starting at that pair of electrons, this is going to become this new nitrogen-hydrogen bond, all right? But then I also have to break that existing oxygen-hydrogen bond and give that pair of electrons to that oxygen atom there. Cool. All right, so real quick, just for the sake of being good about our functional groups here, reviewing what we can. Double bonds, what do we call those in terms of our functional groups? So these would be alkenes. What about this carbonyl group located right next door to a hydroxyl group? What are those? Carboxylic acids. All right, and then this one, I got to make it an organic molecule. I'm going to replace one of these hydrogens with a CH3. Now it's an organic molecule with this nitrogen functional group. What do we call those? Amines. We haven't really talked about them. We experienced them a little bit in the lab. They're the ones that stink really badly. All right, we haven't talked about them. We will this semester. But yes, these are amines. All right, and then lastly, just some more terminology here. We got one more reaction that we're going to go over. This is between a ketone, like acetone, and water. I'm going to tell you that this carbonyl carbon right here is the electrophile in this reaction. And I'm going to tell you that this oxygen right here is the nucleophile in this reaction. All right, so what is that supposed to do for you? Well, remember, this is the basis of pretty much every reaction that we encounter in organic chemistry, is there's one thing which we call the nucleophile that has a lot of electrons, and it attacks this other thing which we call the electrophile that doesn't have a lot of electrons, right? So what you got to remember is nucleophiles attack electrophiles. Okay, so if I tell you that this is the nucleophile in the reaction and here's the electrophile, you know that nucleophile has to attack that electrophile. Okay, using those electron pushing arrows. All right, now before we go on, before we finish this off here, let's just take a second here. This is going to be what? Bond breaking or bond formation? Bond formation, okay? So if I form that new bond to this carbon atom here, what's going to be the problem? I got too many electrons. And again, we're going to study these carbonyl groups a lot. And what we're going to see over and over and over again are those carbonyl carbons playing the role of an electrophile. But there's always a second step that happens concurrently, which is this pair of electrons is going to jump up onto that oxygen atom. All right? So that carbon doesn't illegally break its octet rule and have too many bonds. Okay? So see if you can't finish this off. What's the product of this step in our mechanism here? Yeah. All right, pay careful attention to your charges. Charges are kind of an easy thing to mess up in this particular step here. All right, so I have my one oxygen, that double bond broke. So now it's got 3 lone pairs. That water, notice that it didn't lose any of those hydrogens, not yet at least. Maybe it does at an additional step in this mechanism, but in this first step, those hydrogens are still there. So I'm going to draw my oxygen with both of those hydrogens. How many lone pairs should be on that bottom oxygen? Just 1, because it's got 3 bonds. All right, so I got 1 oxygen with 3 lone pairs and 1 bond, so what's the formal charge? Minus. At the bottom, I have an oxygen with 3 bonds and 1 lone pair, so what's the charge? +1. Okay, and of course it wouldn't stop here. You got both oxygens mad, right? So there'd be this transfer of, this hydrogen would move over. But in our first step here, this is our mechanism. Actually, let's finish this off. Here. This is going to reach down, grab this. So finish this off for me. Oops. All right, this type of step in a reaction mechanism we would call a proton transfer, because all that's really happening is we're moving a proton, moving a hydrogen from one atom to another. Such that now we have these two OH groups in our product. And whatever, we'll study these reactions in more detail when we get there. Importantly, though, is this terminology, nucleophile and electrophile. We use this all the time in organic chemistry. A nucleophile, importantly, is the electron-rich species in a reaction, something that has a bunch of electrons. It likes to react with things that don't have a lot of electrons, so that's our electrophiles. These are electron poor. And because the base of our arrow is always at a pair of electrons, we will always see the base of the arrow at the nucleophile extending or attacking that electrophile. Cool. All right, we're done there. Welcome back. All right, crash course and everything first semester that we're going to need carrying forward here. Again, if there's any point where you're like, oh man, I do not remember that at all, you have some practice assignments that you'll have for homework, and that's your chance to go back and review. If you remember everything, fantastic. But yeah, if you don't, make sure to spend some time doing some review so we can go forward here. Okay, we will start lab here at whatever it's supposed to be, 2:30. All right, and yes, we will pick it up then. Cool. Break.